Welcome to the lecture series on data structures. In this lecture, we talk about deletion of a node in a binary search tree. In the previous lecture, we talked about creation of the binary search tree and searching for a key value and insertion of a node at appropriate location in the binary search tree. Now, when it comes to the deletion of a node, usually we start with the root node and trace through the binary search tree until we find the suitable node or node that is depicted to be deleted. Once the node is found, there are three cases. Either the node may be a leaf node, and the deletion of the node is a straightforward case. Simply we can delete the node if it is a leaf node. If it is not a leaf node, again there are two possibilities. Either there may be a left subtree existing for that node and no right subtree, or there may be a right subtree which is existing, there is no left subtree, or the third case is there are left and right subtrees of the node. So we need to look into all the three cases. Let us see one by one. The binary search tree. The input to the algorithm is tree comma val, where tree is the starting root node of the tree, and val is the value to be deleted from the binary search tree. Initially, let us assume that we are not deleting the root node. We need to deal it with this separately. If data of the tree is not equal to val, if it is not a root node, then we need to search the suitable node to be deleted, and we need to identify the case. So that search process can be completed with a separate functionality. We call that binary search of tree. So we conduct search on the tree through the algorithm binary search of tree. We'll talk about that algorithm later. And that algorithm returns two values, temp comma parent. Temp is the node that is to be deleted, and the parent is the parent node of the node that is to be deleted. Once the algorithm returns temp comma parent, then we need to delete the value. There are three cases as we discussed in the previous slide. In the first case, we need to delete a leaf node. If it is a leaf node, how to delete this? How do you identify the leaf node? Is if the left child and the right child of the temp are equal to null, then it becomes a leaf node. Then simply if left child of parent is equal to temp, this node to be deleted may be a left child or a right child. In either case, if left child of parent is equal to temp, then keep the left child of parent as null and delete the temp. Else, if it is right child of the parent, then right child of parent shall be made null and temp has to be deleted. Now this is one case. The other case is deleting a node which has a left subtree but has no right subtree. In this case, simply we need to replace the temp value in the parent node with the left child of the node. So we'll observe that if left child of temp not equal to null and right child is equal to null, in this case, again we'll check whether the temp is a left child or right child. So if right child of parent is equal to temp, that means the node to be deleted is a right child of the parent. Then right child of parent is taken as left child of temp, because tree is present on the left child of temp, and delete temp. Else, if left child of parent is equal to temp, then left child of parent is equal to left child of temp and delete temp. So in either case, we can attach the child of temp to the parent, and temp can be deleted. And the other case is deleting a node which has a right subtree and has no left subtree. So again in this case, we will observe if that can be observed if left child of temp is equal to null and the right child of temp not equal to null. Again, there are two possibilities. If right child of parent is equal to temp, the node to be deleted is right child of temp. In this case, right child of parent is equal to right child of temp. We're attaching the right child of temp as the child of parent. Delete temp. Else, if left child of parent is equal to temp, if the node to be deleted is left child of the parent, then left child of parent is taken as right child of temp, because there is no left for the temp. Is attached, and then node to be deleted, temp to be deleted. These are the two cases in which either there is a a left subtree or a right subtree for the given node to be deleted. Now, deleting a node which has both left and right subtrees. This is a peculiar case where if left child of temp not equal to null and right child not equal to temp, and then again two possibilities, a left child of parent is equal to temp. So in this case, there are two ways we can do this. Here I am presenting one way. We need to identify the maximum value in the left subtree, and wherever node is there having the maximum value, for that node the child of the temp has to be attached. So temp1 is equal to max of left subtree. It's again a separate functionality to identify the maximum value existing in the left subtree of the temp. It returns the address of the node which has maximum value in the left subtree of temp. And then once it is identified, right child of parent is taken as left child of temp, and right child of temp1 is taken as right child of temp, and delete the node. So once that is right child, maximum value is identified, for that we are attaching the child of the node. This is the scenario. Else, if left child of parent is equal to temp, the other case is the left child of parent is equal to temp, then we can identify the minimum value in the right subtree. We will identify the minimum value in the right subtree and attach the child of the temp to that. So temp1 is equal to min of right subtree of temp. Again, a functionality is there. We need to talk about that later. It identifies the minimum value existing on the right subtree of the temp. So I give it to the temp1, and then left child of parent is equal to right child of temp. So whatever child is there for the temp, that has to be attached as the left child of the parent, and left child of temp1 as left child of temp. The existing left child of temp is attached to the left child of temp1, and then temp can be deleted. So this is a broad algorithm. We'll again analyze this in the subsequent slides. Now we'll look into the deletion process of a leaf node in detail. We'll try to trace the algorithm. Given the binary search tree here, if you want to delete 8 from the binary search tree, so first we check if data of the tree is not equal to val. 2040 is the root node here, and value at data 2040 is 15, which is not equal to 8. So then we'll go to the search, binary search algorithm has to be run on that, which returns two values. One is temp and parent. Temp is the node which is to be deleted. 8 is present in 2046, that is identified as temp, and parent of that is 2042 is identified here. So once temp and parent are identified, deletion has to be processed. Again, we'll check whether the left child of temp is equal to null. So and the right child of temp is equal to null. The node to be deleted is having left and right children as null, so it's an indication that it's a leaf node. Then we need to check whether this is the left child of the parent or right child of parent, and that can be achieved by if left child of parent, left child of 2042 is equal to 2046, so this forms a left child. Then what we need to do is we need to make the left child value of 2040 as null. So left child of 2040 is null. Once we do this, the link is disconnected, and we can delete the node 2046. So this is how we can delete the leaf node. Now we look into the deletion of a node which has a left subtree or right subtree. In this case, we'll trace the part where the node that has to be deleted has a right subtree. Now if I want to delete 37 has a right subtree which has no left subtree. If I want to delete that, if we follow the algorithm again, delete tree comma val, delete 2040 comma 37. First we observe that data of 2040 is equal to 15, which is not equal to 37. That is, the node to be deleted is not the root node. Then immediately it checks binary search is performed to locate the node consisting of value 37. And that algorithm returns two values. One is temp and parent. Temp is the node where the value is present, and parent is the parent of that node. If we perform that on the given tree, 37 is present in a node where the value is 2072 is the temp and the parent of that is 2048. So binary search returns two values 2072 and 2048, temp and parent. Once the node is identified, we need to check into which case it falls. That means whether this 37 is the right child of the parent or the left child of the parent is the first observation. So if here two cases, left child of temp not equal to null and right child of temp is equal to null is not the case. The other one is left child of temp is equal to null and right child of the temp not equal to null. So the node has a right subtree. In this case, again, if right child of parent is equal to temp, this 37 is the right child of 30. So the case is true. Right child of parent is equal to temp is true. Now that is observed here. Left child of 2072 is null and right child of 2072 is not equal to null. That's a right subtree is there for this. And right child of 2048 is equal to 2072. That means this is the right subtree for the parent. In that case, what do? Right child of 2048 shall be linked to the child of right child of temp. So right child of 2072. So that is 2088. So 2088 is placed in right child of 2048. So that that right child now 2072 can be deleted. So delete 2072. That means the value 37 can be deleted from the node, and whatever be the right child of that is linked to the as the right child of the parent. The last case is deletion of a node which has both left and right subtrees. In this case, in the given example, 30 is one such node which has a left subtree as well as a right subtree. Now if we want to delete 30, we need to adjust the left subtree and right subtree. How can we do that? Here is a descriptive procedure that is depicted here. When parent is there and left side triangle indicates a left subtree of that, and temp is there, which is the right child of the parent, and it has left subtree and right subtree. Now if this temp has to be deleted, then we need to observe the LST, left subtree of the temp, and identify the maximum element or the largest element that is present in the left subtree, identify that, and attach the right subtree of temp as left subtree of the highest node in the LST, and this LST is added at the right child of the parent. Why this has to be done? Means if you observe, all the nodes in the left subtree of parent are less than parent, and all the nodes that are right of parent are greater than parent. So whatever elements are there in the LST of temp are already greater than parent. So they can be added as the left child of the parent, right child of the parent, so that they are already greater than parent. And RST of temp, right subtree of temp, is greater than the values of temp, and they are already greater than the values of the LST of temp. So they can be added as a right subtree of the last highest vertex of LST. So this satisfies the conditions of the binary search. It still satisfies the binary search tree conditions, and the temp can be deleted easily. This is one method. Similarly, if the node to be deleted is the left child of the parent, then again LST is elements of LST are less than temp, temp is less than elements of RST, and all these things are less than parent. In this case, if this is to be deleted, what we do is we can identify the least element of the right subtree of temp, least element of right subtree of temp, and to that least element this left subtree can be attached, so that the binary search tree conditions are not violated. This is one way of doing. The alternative approaches are also there. In this case, the algorithm depicts this process. As I told you, the alternative procedures are also there. If you want to delete the temp, which is the right subtree of parent, instead of moving LST above RST, we can move RST up and LST as the left child of that. So for this, what we do is we'll identify the least element of the RST and to that least element LST can be added as a left subtree. Similarly, when temp is a left child of parent, instead of moving RST up, we can move LST up also here. We can identify the largest element of the LST, and for that largest element we can add RST as the right subtree. In both the cases, if you observe, if you want to move that LST, left subtree up, we need to identify the maximum element of the left subtree. Similarly, if you want to move the right subtree up, we need to identify the least element of the RST. So for that we have functionalities are added here. Max of left subtree of temp is there. We start with the left child of temp. Temp1 is equal to left child of temp. While right child of temp1 not equal to null, we need to traverse through the left subtree so that we can reach the maximum, because maximum elements will be there in the right subtree of LST, right part of the LST. So we keep on moving towards the maximum possible right side. That is why while right child of temp1 not equal to null, we keep on moving. Temp1 is equal to right child of temp. We keep on moving, and once we reach the rightmost point, return temp1 is returned. Similarly, in case of min of right subtree, we keep on move to the leftmost point and return the leftmost node. So temp1 is equal to right child of temp, and while left child of temp1 not equal to null, we'll keep on moving. Temp is equal to left child of temp1, and once that child of temp1 is equal to null, that's an indication that's the lowest value. So we'll return temp1. So min of right subtree can be returned from this. Similarly, we are talking about binary search of given tree and val. In the previous slides, we have used this binary search tree, which returns two values. One is temp and parent. For that also we have the algorithm here. We start with the temp searching. For the searching, temp is equal to null, parent is equal to null initially. If tree is equal to null, that means the given node, the tree itself is not there, null, then nothing to be returned. Return temp and null as null. Else if data of tree is equal to val, that means if the root node itself has a value present, then we return temp is equal to tree, parent is equal to null, temp1 is equal to tree, and we can return those values. While data of temp1 not equal to val, then we need to traverse. If data of temp1 is less than val, that means val is on the right subtree, parent is equal to temp1, temp1 is equal to right child of temp1. So they are updated. And else if data of temp1 is greater than val, val is on the left side, so parent is updated as temp1, temp1 is updated as left child of temp1. And we keep on doing this in the while loop until data of temp not equal to val. Once that is found, temp is equal to temp1 and return temp comma parent. So once that node is found, we can return the temp and parent value. So this is how we can run this algorithm to satisfy all the three cases. Definitely, binary search tree is one of the best representation of the data when data is ordered. And when it comes to the traversal, the time complexity is also much better when compared with the other traversals. But however, there are certain drawbacks in the binary search tree also. While insertions and deletions, when there are large number of vertices, on deletions, we may arrive at a scenario where only right side children are present and no left children are present. So starting from the root node to the last node, everywhere it is only a right child. Similarly, or everywhere it is only a left child is attached and no right children is there. They are called right skewed and left skewed trees. When such a scenario occurs, the effectiveness of binary search tree is lost. Why? Because whenever we want to search an element, it is as good as searching the entire number of elements present. So order of n, we call it as order of n. So the speciality of the binary search tree is lost in such cases. This is one of the drawbacks of binary search trees.